Before sitting down at the table, I had considered that there was one chance in two that my adversary was not honest. An absurd hypothesis, because in that case I should certainly not have played with him, and this explains the absurdity of the conclusion. The function on the a priori probability was unjustified, and that is why the conclusion of the a posteriori probability led me into an inadmissible result. The importance of this preliminary convention is obvious. I shall even add that if none were made, the problem of the a posteriori probability would have no meaning. It must be always made either explicitly or tacitly. Let us pass on to an example of a more scientific character. I require to determine an experimental law. This law, when discovered, can be represented by a curve. I make a certain number of isolated observations, each of which may be represented by a point. When I have obtained these different points, I draw a curve between them as carefully as possible, giving my curve a regular form, avoiding sharp angles, accentuated inflections, and any sudden variation of the radius of curvature. This curve will represent to me the probable law, and not only will it give me the values of the functions intermediary to those which have been observed, but it also gives me the observed values more accurately than direct observation does. That is why I make the curve pass near the points and not through the points themselves. Here then is a problem in the probability of causes. The effects are the measurements I have recorded. They depend on the combination of two causes, the true law of the phenomenon, and errors of observation. Knowing the effects, we have to find the probability that the phenomenon shall obey this law or that, and that the observations have been accompanied by this or that error. The most probable law, therefore, corresponds to the curve we have traced, and the most probable error is represented by the distance of the corresponding point from that curve. But the problem has no meaning if before the observations I had an a priori idea of the probability of this law or that, or of the chances of error to which I am exposed. If my instruments are good, and I knew whether this is so or not before beginning the observations, I shall not draw the curve far from the points which represent the rough measurements. If they are inferior, I may draw it a little farther from the points, so that I may get a less sinuous curve. Much will be sacrificed to regularity. Why then do I draw a curve without sinuosities? Because I consider a priori a law represented by a continuous function, or function the derivatives of which to a high order are small, as more probable than a law not satisfying those conditions. But for this conviction the problem would have no meaning. Interpolation would be impossible. No law could be deduced from a finite number of observations. Science would cease to exist. 50 years ago physicists considered, other things being equal, a simple law as more probable than a complicated law. This principle was even invoked in favour of Mariott's law as opposed to that of Regnault. But this belief is now repudiated, and yet how many times are we compelled to act as though we still held it? However that may be, what remains of this tendency is the belief in continuity, and as we have just seen, if the belief in continuity were to disappear, experimental science would become impossible. 6. The theory of errors. We are thus brought to consider the theory of errors, which is directly connected with the problem of the probability of causes. Here again we find effects, to wit, a certain number of irreconcilable observations, and we try to find the causes which are, on the one hand, the true value of the quantity to be measured, and, on the other, the error made in each isolated observation. We must calculate the probable a posteriori value of each error, and therefore the probable value of the quantity to be measured. But, as I have just explained, we cannot undertake this calculation unless we admit a priori, i.e., before any observations are made, that there is a law of the probability of errors. Is there a law of errors? The law to which all calculators assent is Gauss's law, that is represented by a certain transcendental curve known as the bell. But it is first of all necessary to recall the classic distinction between systematic and accidental errors. If the meter with which we measure a length is too long, the number we get will be too small, and it will be no use to measure several times. That is a systematic error. If we measure with an accurate meter, we may make a mistake and find the length sometimes too large and sometimes too small, and when we take the mean of a large number of measurements, the error will tend to grow small. These are accidental errors. It is clear that systematic errors do not satisfy Gauss's law, but do accidental errors satisfy it? Numerous proofs have been attempted, almost all of them crude paralogisms. But starting from the following hypotheses, we may prove Gauss's law. The error is the result of a very large number of partial and independent errors. Each partial error is very small and obeys any law of probability whatever, provided the probability of a positive error is the same as that of an equal negative error. It is clear that these conditions will be often, but not always, fulfilled, and we may reserve the name of accidental for errors which satisfy them. We see that the method of least squares is not legitimate in every case. In general, physicists are more distrustful of it than astronomers. This is no doubt because the latter, apart from the systematic errors to which they and the physicist are subject alike, have to contend with an extremely important source of error which is entirely accidental. I mean atmospheric undulations. So it is very curious to hear a discussion between a physicist and an astronomer about a method of observation. The physicist, persuaded that one good measurement is worth more than many bad ones, is pre-eminently concerned with the elimination by means of every precaution of the final systematic errors. The astronomer retorts, "But you can only observe a small number of stars, and accidental errors will not disappear." What conclusion must we draw? Must we continue to use the method of least squares? We must distinguish. We have eliminated all the systematic errors of which we have any suspicion. We are quite certain that there are others still, but we cannot detect them. And yet we must make up our minds and adopt a definitive value which will be regarded as the probable value. And for that purpose it is clear that the best thing we can do is to apply Gauss's law. We have only applied a practical rule referring to subjective probability, and there is no more to be said. Yet we want to go farther and say that not only the probable value is so much, but that the probable error in the result is so much. This is absolutely invalid. It would be true only if we were sure that all the systematic errors were eliminated, and of that we know absolutely nothing. We have two series of observations. By applying the law of least squares, we find that the probable error in the first series is twice as small as in the second. The second series may, however, be more accurate than the first, because the first is perhaps affected by a large systematic error. All that we can say is that the first series is probably better than the second, because its accidental error is smaller, and that we have no reason for affirming that the systematic error is greater for one of the series than for the other, our ignorance on this point being absolute. 7. Conclusions. In the preceding lines I have set several problems and have given no solution. I do not regret this, for perhaps they will invite the reader to reflect on these delicate questions. However that may be, there are certain points which seem to be well established. To undertake the calculation of any probability, and even for that calculation to have any meaning at all, we must admit, as a point of departure, an hypothesis or convention which is always something arbitrary about it. In the choice of this convention we can be guided only by the principle of sufficient reason. Unfortunately, this principle is very vague and very elastic, and in the cursory examination we have just made we have seen it assume different forms.